Hi everyone, Roy here, Synthux Academy. Um, if you're not familiar with our channel, we are a non-profit based in Rotterdam in the Netherlands. We are running all sorts of activities on synth design, programming, engineering, and synthesis. In particular, we're trying to reach musicians and to teach how to build your own synths because it's fun and very rewarding. Um, there are a lot of engineers in our community on Discord. There are a lot of designers. And what we're doing is we're creating all sorts of activities like workshops. There's actually coming up one in Boston in Synth Cube very soon, not announced yet. Um, we create all sorts of kits like this thing that you see here, all sorts of boards that are um, like a place for you to design your own instrument. And we've been doing it for about a year now with these kits. So Vlad, for example, the guy that you're about to see, if I'll manage to do my this guy.
Hey.
um, Vlad and I worked on this synthesizer. You just see the front panel here. This is the heart of it. And Vlad is an engineer with, I think, over 15 years of experience working in C++. So he was doing all the engineering and all the sound and programming of this. And I worked also with a student of mine on the design of this. Um, so the design actually uses touchpads, and the lesson that we're going to have today is about these touchpads. If you look at this board, um, this is a front panel of a synth. If you look at the back side, you can see that there are these pads where you could solder pins. And when these pins are connected to this board, they interact with a microcontroller, which you don't really see on this one, but you can see it here. And when they interact with the microcontroller, you can see that there are these traces that go into the pads in the back. So when you touch on something, it will do something. What we're going to do today is we created a smaller version of this, a more broken down version of this, so we could understand how this thing is designed internally and how it is programmed. Um, yeah, I wanted to give a shout out to two of my students that made these beautiful stickers. Gonna drop links to their Instagram accounts because I think they're just amazing, and they made these when doing an internship with me. Yeah, these are just really cool. So this is by Sophie Bollman, and this is from Kasha. Um, and yeah, I'm gonna send the links right after. Let's get started. So I'm gonna send you directly to here, and I'm gonna shift this screen so you can see me and you can also see Vlad. And Vlad is going to explain everything. So if I need to jump in and explain or like clarify some stuff, I'm going to do it. Sometimes I do it because I'm not an engineer, so a lot of the things that he explains, I'm like, hold on. I need a bit more clarification on this. So I might stop him for a second. You can also stop him. I'm going to look at the chat. So if you have any particular questions, then feel free to drop them in the chat, and then I'll bring these up to him to clarify some of the things. Um, Vlad, thank you so much for taking the time for this. Maybe give a short introduction of who you are, and we can get started.
Yeah, thank you for having me. Yeah, I'm Vlad. I'm doing software. Um, by day, I'm doing actually mobile software mostly, and yeah, by night I do all these strange sound machines. And today we will talk about one of them. But yeah, before we go into instrument itself, I would probably first go a little bit through the basics of this touch sensor, how it's connected, how some like basic setup works, and then being equipped with this, we can look into the instrument. The instrument itself, by the way, um, is built based on the arpeggiator synth that we talked about last workshop or one before. Yeah, so I will probably not go too deep into the internals of the arpeggiator itself, and so uh, please watch this previous episode. There we go through this with like really in depth. And yeah, so we today have a little bit more time to focus um, on the controls, yeah, on touch sensor, and also we will see how the structure in the code simplifies changing, uh, because original like initial design was without any touch sensor. It was just uh, one pod that like selected some set of notes that arpeggiator played, and now we have like enhanced version, yeah, which allows a little bit more control and really like experience of playing an instrument. So yeah, let's start with just sensor itself. To do this, I will switch now my camera, so you will hear me, but not see me. Hopefully it switches now, right?
Yeah. Perfect.
Everything is good. Yeah. So NPR 1-to-1. It's actually it comes in different configurations, yeah, different breakout boards. The touch sensor itself is this really can I make it this really tiny square, yeah, so this is basically the NPR 1-to-1 itself. Yeah, all around it is just a breakout board, and they come in different like different forms. So this one is like most common, I would say, and like you can get this from other fruit, like this configuration. This particular one is just some no name from Amazon. Also works, except one pin somehow doesn't work properly. Yeah, so if you want something really robust, it's like worth double checking all the time. Yeah, every electronics can be faulty, and this one is from Adafruit. It's designed to be used together with crocodile clips. So I put here these screws because it's easier to touch, like this when it's not flat. Yeah, but originally there are like holes, like big enough holes on on every pin. Yeah, so you can actually use crocodile to connect to it. So it's good for prototyping. What this thing doesn't have comparing to this, it doesn't have IRQ pin. I will explain in a moment what is it. And for address, it it can switch only between two addresses. This one can switch between four, but this functionality doesn't work on this particular board, so it's faulty. So I will show on the second one. So instead, it has this STEMMA QT connection, uh, which can be found on many other fruit products. So pretty convenient thing for like quick prototyping. So I use it also a lot. So if we Connection, it's connected through I2C, inter-integrated circuit. So we need 2 pins, one pin for SCL, one SDA, and 2 pins for power. Yeah. So if we're talking about Daisy, Daisy has 2 I2Cs. So one is on pin D12 and D11, as far as if I'm not mistaken, and second one is just next to it. Yeah, 13 and 14. So yeah, given that that you have like this address can be switched, so every the board can have 4 different addresses. So on this inter-integrated circuit, every device has a unique address. Yeah, should have unique address, and for MPR 1-to-1, you can select one of 4 addresses, which means that you actually can connect up to 4 boards to one I2C channel. So let's look into the how to connect it, how to use it with Arduino. In this case, I just open it. So once you install, first you need to install library. So if we go into libraries tab, I have it already installed. This Adafruit MPR 1-to-1, it works basically with any board, generally. There is some other libraries I didn't try it yet, but yeah, this one actually works pretty fine. And so once you install this library, you have also in examples, you have Adafruit MPR 1-to-1. So this brings actually this basic example. I modified it a little bit already to demonstrate some other functionality, but it's generally like not too different from what you have in like basic example. Yeah. So how does it work? You create this Adafruit MPR 1-to-1 instance in this case, and then in setup function, probably I should make it a little bit bigger, right?
Yeah,
It will be
That's
better. Yeah. And yeah, so this is basically the initialization of this sensor itself. So by default, sensor has this address 5A, and here in this command they even suggest how to change this address. So if the address pin is connected to one of remaining pins, it actually changes address to B, C, and D. So, and basically to initialize it, you only need to do this begin, call this begin with address. All the rest is just more or less status. Yeah, so it will complain if it cannot find if something with wiring. And then in a loop, we just query all the time the sensor for the status. So if we let me try to run it. If I restart it, what's going to happen? Yeah, I already just to save time, I already uploaded this example to Daisy. So I just restarted it. So it found MPR, yeah, and if I touch those pins, yeah, it just shows that it's touched. Yeah, and how it's happening, the status of the pins is actually delivered as one integer, which and every bit of this integer is responsible for particular pin. Yeah, so to read those pins, we need here bitwise operations. So if we look here, there are this is like just two variables: current touched, last touched. So it's like compares all the time previous state with the current one, and that's how it can say if it was touched or not. Yeah, so we can actually catch the moment of this change, yeah, from touched to not touched. And yeah, so here we have bitwise AND, and this BV is just a macro which is defined somewhere on the top. Yeah, here. So this is basically it's just a shift. Yeah, if we say that if we have something like have some number, I don't know if it's 16, probably more. So what would mean that one is shifted by like 1, let's say, it will be, oh sorry, it will be like here, or then if you shift it by 4, it will be here. Yeah, so it's actually position of the pin, and this shift is actually corresponds also to the pin on the board itself. Yeah, so that's how you read it. Yes, so we say that we want pin pin 0, let's say it will be on 0 position. If it's and bitwise AND, it's basically if you have two numbers like this, if both bits are, it actually doesn't even matter. So what is important that corresponding bits are 1. Yeah, in this case, this bitwise AND will be also 1 here. So it will return, in this case, it will return like this. Yeah? So 1 and 0 will give 0, and 1 and 1 gives 1. That's basically how we detect that this thing is touched. And if we want to do, let's say, in some cases, you want to know, like, you want to use like 2 pins and check that they touched simultaneously. Yeah, then you of course can always create something like this. Yes, some mask like this. Let's say this is your state, and this is what you check against. And this also, so you can also catch this way if multiple pins are touched. And how to create this mask is bitwise OR operator. So let's say we have one number like this, another integer like this, and this is A, let's say this is B, and bitwise A and B, or B, sorry, will give actually this number. Yeah, so we can combine pins and check against multiple pins at the same time. I will show in a moment why we want to do this, why it's somehow useful. So yeah, otherwise that's all the basics about this. Yes, how it works. So you just read this integer, you check pins, and looking on these pins, you know if it's touched or not. Yeah.
Yeah, that's great.
Before we go further, if you have any questions.
Actually, Ivan had a more general question just before you started. He was wondering about the microfreak, because like the touchpads on the microfreak, do you know if it's actually using a similar sensor or something completely different?
I don't know. If in this case, it's hard to say. I didn't look there, but it might be that it because I mean this sensor is really widespread and it's like it proven to work good, so it's likely that it's, but no guarantee.
Yeah. Okay. Cool. Yeah, guys, if you have any specific question or if you want us to dive into certain parts, feel free to ask. Otherwise, yeah, Vlad, just continue with your own plan.
Yep. Okay. So uh, now just a quick mm, I want just to quickly mention this pin, IRQ pin. Yeah, so I connected here this white wire. It's IRQ pin to, and I connected it to pin D10. So what is this? It's interrupt request pin. So what does it mean? That we can register interrupt. Interrupt is a so what is interrupt? It's actually what name suggests, an interruption of the normal program flow. So loop, this circling through the loop all the time. This is actually normal program flow. That what microcontroller does all the time. Yeah, so it just spins this loop until it gets some interrupt. And interrupt can be it can be some internal interrupt. It can be interrupt like this, like for instance. From the from some device, yeah, that, and when this interrupt comes, it stops this like normal loop and switches to the function that is registered as a handler to handle this interrupt. Yeah, so, and I just prepared here, I will comment out this loop completely, what we do in a loop. And instead I have here the function, just added function, which is which internally does exactly the same. I just copied it from the loop. Yeah, so it's, oh, sorry, it's exactly the same. And so this is just a function that takes no arguments, and name basically doesn't make any difference. And in Arduino, we have this function attach interrupt, and we say that we want pin D10. Yeah, so I connected it here to D10, and this is actually the name of the function on IRQ. Yeah, so here. And mode low. So low, what does it mean? Is that this IRQ, how does it work? It actually, it requests interrupt when it goes low. Yeah, so otherwise it pulled up. Yeah, and if we, hopefully I can now, it will take a little bit of time to compile and flash it. Yeah. So now if I touch it, it also reacts. Yeah, so it does everything that everything the same. Yeah, so but we are not spinning, we don't like ask all the time the status in a loop. Yeah, we don't do it. As great as it sounds and looks, it's good for some applications where we don't have like audio callback, let's say. Why? Because here we don't control interrupt priority. And without controlling interrupt priority, we can easily get into the situation when interrupts will conflict between each other. And let's say in libdaisy, as far as I know, there is even no possibility to attach interrupt. So it's designed to use polling. Yeah, so just ask all the time in a loop. But anyways, for some applications, like if you do some interactive applications and you want something like, you don't want to spin the loop all the time, you can do it. Yeah, so That's basically what this RQ pin actually does. It actually requests interrupt. Yeah, why I was talking about this combining of different pins and asking. The thing is that for there is a technique called multiplexing. For the and particularly it's useful with this um, in this case, in case of touch sensor. So we have 12 pins, yeah, only 12 pins, and which means that we can use just more or less like 12 pads, yeah. But in fact, we can use way more pads with multiplexing. And how it works actually, every physical every, or let's put it another way around. Two physical pads represent like one logical pad. Yeah, so we imagine that we have like these two pads on PCB. Yeah, so yellow and orange, and we can do like really many of them, and all the yellows they connected to their own like output, and all oranges also connected. Every row connected to its output, and every column is also connected to its particular output, which is, and let's say then we connect it to our pins, so to 0 1 2 3 4 5 6 7. So in this case we use only 8 of them, so we use 8 pins, but we got already 16 pads actually. So if we place them like close together, yeah, those like pairs, when you touch them you will touch like balls. And then logically what you do, you just check that if you checked, let's say, pin 0 and 4, it's like pad number 1, 0 and 5, pin number 2, 0 and etc etc. And which means that with MPR with 12 pins you can have this matrix 6 by 6, which gives you 36 pads. That's way more than you expect probably originally. And because you can connect up to 4 boards to one channel, yeah, you can have 24 by 24, which gives you 576, I guess, pads. Yeah, so it's like you can do really like something really interactive with it. And yeah, so with this, what I can probably also show you actually how to connect like multiple, yeah, if you want to connect multiple MPRs. So to do this, I will do a little bit of live coding. So instead of just one sensor, I just defined array of 2, and last touched will be also array of 2, because I have only 2 boards. Yeah, and we let's say we do it just, I will just just do it like this, and then we can here. So this is our initialization. I will just copy and say 5b. So we will have 5 at index 0. We have 5a, which is this smaller one, and 5, and at index 1 we will have 5b, which is this other fruit, big one. Yeah, and here we need just a loop inside the loop. We say in j, oh sorry, j equals and j less than 2, and So we will just iterate through, and yeah, here we will finish. And now we do here touched J, cap J, so we can easily look through multiple boards at the same time. Yeah, so just iterating through the array. We need to add here also. Okay, and finally here. Hopefully I didn't do a mistake there, and it's going to work. And now I need to connect them, so I connect them just in parallel. Power is already connected, so I just connect this SDA to SDA and SCL to SCL to actually to exactly the same pins.
Just to clarify, I squared C, so I2C that Vlad refers to here, is a digital protocol that allows you to chain multiple sensors on the same two pins. So he's now connecting two sensors to the same two pins on the daisy in parallel.
Yes, that's at least this is the intent. Just a second. I just need to check that it's actually built. Yes. Okay, let's try. Hopefully it works. Okay. No. Sorry. Once again. Yeah. I just. Yeah. Okay. So second one, it doesn't find. So probably I did something wrong. So when I tried to do this, it worked actually. I just don't want to solder it permanently to B. So I thought, okay, now it's found. Okay, so if I touch this, it works. If I touch this, it works. Yeah, so I have two of them. Yeah.
So you just had to reset the daisy?
Yeah, and I had to just hold it better. Yeah, this.
Right.
So this pin is here. Yeah, and yeah, I just I just don't want to solder it permanently. So I'm usually like checking it like this. Yeah. So connecting.
Just a quick question, follow up, because you're actually now connecting two sensors, and that's a lot of touch controls.
Yeah.
There was a question, a follow-up question from Ivan about the microfreak, because it actually has more functionality than just on-off, right? It has some sort of velocity, and it's a bit more refined. But this is only an on-off sensor.
Yes.
If I understand, like if I'm just doing some logic in my head, it would make sense to maybe have multiple pins connected on the same pad, and then when you touch, it actually feels like there is velocity, because you're now it would detect if you're touching one or two of them or three of them or four of them at the same time, and then by this actually give you velocity, like fake velocity.
Well, so what MPR actually is not only on off. Yeah, so these examples and more or less how it's used in majority of situations, that's actually on and off. But in fact, you can have more information from it. So first of all, MPR can work as a proximity sensor. for this, it requires a little bit of like low level programming. But what you can do with this, it connects all 13, all 12 pins, sorry, together, like multiplexes them more or less, and you get like 13 virtual pad from it, which and you can actually sense like, because if you use like big enough pads in themselves, then you can not feel not only touch but also proximity on like small distances, like up to 5 centimeter, I guess, something like this. But you can do even this. But also, if we just open, let me just open once again the original example. Yeah. So here, if we go like a little bit beyond this, what we just looked at, on this second part of the loop. So what you can get also from this, there is two methods: filtered data and baseline data. So what is baseline? Baseline is like let's say like capacity at the when it's not touched. Yeah. So, and this baseline is always floating a little bit according to documentation. It adjusts to humidity, to temperature, so there is some change happening. And filtered data is actually difference between like capacity without touch and like current. Yeah, so difference between baseline and current, and not even difference, it's just absolute value. And looking on this difference between filtered data and baseline, you can actually detect how it detects actually touch. It has a threshold, particular threshold, and you can even change them. There is a function, as far as I remember, cap. Yeah, set thresholds. Yeah, so there is threshold on touch and threshold on release. And by default, those thresholds are 12 and 6. So it's measured not in some physical units, it's just counts. Yeah. So by default, you have 12 counts of threshold, and you can change it. And if we, let's try to, let me comment this out. Yeah, I guess this one. And let's see what this thing is doing. Yeah. Just let's compile. Yeah, while it's compiling, one more function of MPR that it can do. It can also work as a LED driver and GPIO, like general GPIO. It also requires some tuning, some programming, but this function, there is a document online. There is a documentation from the yes, I guess here. Yeah, so you can also turn the MPR into LED driver, for instance. Yeah, so this function is like less known probably, but it's capable even to do even this. So looks like it's uploaded. Let's see what we get. No, something is wrong. Sorry. Just need to do it once again, probably. Yeah. Okay. So here you have these values. Yeah, for every pin, for every of 12 pins, you have like base and filtered. Yeah, that. And if I touch something, you can see that it changes. Yeah, so I can.
Yeah, so I guess that if you
So
would have a
so
larger pad, then you
yeah, yeah,
wouldn't be
yeah.
able to get.
Currently,
Yeah.
it's a little bit hard to see.
Mm,
So yeah, so you can measure here not only just that it's on or off. You can go a little bit. I don't know if this principle actually, if something like this also used there. I would expect so, but yeah, that would be my guess, that they somehow maybe do some
yeah, and I
additional
guess
things.
that's why you actually have also the ability to change the threshold in the settings, because it might be that you're playing now in a room that has maybe a bit more humidity, so it'll behave differently.
Yeah, I tried to play with it. Still, I mean, at least in usual scenario, this default works really good. I
Mm,
tried to play with it when I was like reusing, combining different pads, and I wanted to have like, if you touch two pads, then you have one function. If you touch them one by one, then you have another function. So I
mm.
wanted to delay a little bit touch detection, yeah, and make it a little bit like slower. So
Yeah,
yeah,
with you mean with Spotify with the recording?
yeah. Um, so yeah,
Yeah, maybe actually maybe just for reference to show you um, what we're talking about. So in the design of this instrument, this is the play button, and
pad, then it clears the buffer.
yeah,
So it's like you can actually, that's the beauty of all this stuff, yeah, that you can really combine it and try different combinations until it actually works for you. So yeah,
so but in a sense,
I'm
you actually don't really need to go into the library itself. What you just explained until now is basically like you're going into the library. But when
uh
we work with
yeah,
Arduino, like we basically have this already built for us, so we can just play with it.
you mean this library from Adafruit?
Yeah.
Yeah, I mean it's already there, and basically that's what I'm using in the instrument also. In Spotify is built on libdaisy. There also there is a library also for libdaisy, so yeah, there I'm also using this Adafruit, but adapted uh, for for libdaisy. Yeah.
Mhm.
So um, yeah, I'm about to switch now to instrument itself. And yeah, if you have some questions regarding all the stuff that we talked about so far, please feel free to ask.
Yeah. So I see that you have there a few classes, ones that we already discussed in a previous episode. The
Yeah,
Vox. That's the maybe let's okay. Yeah, we're going to show it now in the visualization. Cool. Yeah.
yeah. So yeah, it's actually exactly the same instrument that we shown in previous episode. Um, so what do we have there? We have several classes. One class is called terminal, which actually responsible for input, and then um, ARP. It's actually just an arpeggiator, and the communication between them is like in terms of defined in terms of more or less MIDI protocol. So you have note on with velocity and number, and note on, off. And then we have scale, which converts note number into the frequency, and Vox is simple oscillator, more or less, that just um, uh, then place this frequency. Yeah, and ARP is driven by Metro standard, this standard component from the library, which just produces clock impulses. And yeah, so this is the instrument itself. And what was mainly, like, not mainly, but first what was changed for this workshop that we are doing now, I changed this class terminal. Yeah, so instead of before it was like it was generated some nodes basing on value from pod. Now it listens to the touch sensor. I will show the code just in a moment. And that's basically the what is great about like separating when you design an instrument and separating it into different classes, that if you need to do a change, even like such a dramatic change that you just change your interface, you don't have to look around and change like some stuff in multiple places. You just replace one class more or less, and it works. So I could go with this. I didn't stop there. I changed it comparing to the previous one. I changed it also these two. So scales, I redefined scales. So we have now, like on the touch sensor, we use 8 pins for nodes, and the original scale was way bigger. I don't remember, like 36 nodes or something. So I reduced it to 8, and I defined 3 different scales, and it's possible to switch between 3 different scales. And
Just like
arpeggiator,
just a quick
yeah,
overview. So we have these keys that are the notes, and then we have the scales here. Oh. Yes, and I can really hear the difference. This is latch.
yeah. So those scales are not too different. 2 of them are D scales. One is I guess pentatonic, and another one is Hijaz. I don't remember already, but yeah, I just borrowed it from Tank Drum. And yeah, so arpeggiator got additional function to change note length. In this old example, it was not possible, it was fixed. And also it supports playing this mode as played. Yeah, so the order of notes defined by input. Yeah, previous version was just forward or backward within the sorted note scale. So this is kind of small advances in this, like it's like really more advanced version of the arpeggiator that we shown previously. So let's quickly look into the terminal. Yeah, so it's like represented with this separate class, and I'm using this Adafruit library that we just seen, and I use a standard array for holding nodes. Yeah, so to keep the status of the nodes of the latch works, I use not just a plain array, but this standard container, one of the standard containers from C++ standard library. It's really useful container. It doesn't add overhead, but it's more convenient to work with comparing to the like usual like built-in arrays. So what do we have here? We have initialization. It's just a class constructor, initialization in terms of class itself. Then we have init that actually does what we've just seen. So it just begins with this default address. Here I commented out, this code is on GitHub, by the way. So here I commented out if you want to use like this second I2C on Daisy, if you define via set SDACL to different pins, you can use different channel. It works on Arduino. It doesn't work on libdaisy, as far as I remember. You cannot switch there without like going deep into the library itself. So yeah, so this is basically setup that we've just seen. Here I use callbacks to send node on and node off, and also scale select. So when scale changes, when we touch one of the pins that controls the scale of the instrument, it calls this callback. Yeah, so principle of callbacks is basically the same what you've seen in audio callback. Yeah, so it's just a function registered to be called on demand. And yeah, so just some basic getters like is latched. And yeah, so this is basically process function. It's called from the, if we look here in the loop, it called here. So it's basically the same as what was in this example. And here I just iterate through all the pins, and then pins 0 to 7 work as node pins. So for them I set node on off, and also write it into this hold. Hold array is basically again for latch. Yeah, so when I touch, if latch is on, I write into this array, and it just stays there. Pin 8 is actually latch pin, so it turns on off latch, and 3 remaining pins, so 9, 10, 11, they actually select different scale. Yeah, so it's not that different from what you've just seen in the example. Yeah, it's and I actually wanted to keep it like this, as close as possible to the example without too much modifications, because if we look on, let's say, code from Spotify, there are more like stuff there happening. But yeah, that's basically what this terminal does. And then in scale, I have just predefined these predefined scales, just frequencies. Oh yeah, here I left comment for myself, in case I forget which scale it is. And yeah, frequency at just takes the corresponding frequency at index at it's just a node number, and the scale index switches between 3 of them. And here I also use this this standard array, and it's actually two-dimensional array. So it's array. So this like scary notation. It's basically usually what you have. Let me copy it here somewhere. Yeah, so how we define plain array. Usually we say float, let's say a, and here we have size of the array. And in this case, float and size goes in this, like in these brackets. Yeah. So, and for two-dimensional arrays, it's actually the type of the element is array itself. Yeah, so array within array. So array of 3 arrays of 8 in this case. Looks a little bit like verbose, but otherwise not too like advanced, I would say.
Just a little bit.
Yeah, I mean, yeah,
No, I mean,
reading C++. That's actually interesting thing about learning C++ and looking on the on existing code. Yeah, that when you look through it, it looks complex, but the thing that you are looking at, it's not the complexity of the language, it's the complexity of the design already. Yeah, so it's complexity of what the guy put there. So if he decides to write it like this, and sometimes it's way longer. I mean, sometimes you have like really crazy stuff there. It looks complex, but it's not language complexity. It's like the guy who wrote it just didn't write it somehow simpler. Yeah, in many cases. So I could also probably define it a little bit, like maybe somehow
yeah, I
somehow
mean,
better.
I can relate. Sometimes you know, you can always optimize more and more with comments and structure and like make things a bit easier to read.
Yeah,
Yeah, so this is actually the first time that I'm seeing something like this, but it is kind of logical. I do see an array. It's just like, what is the STD? What does STD stand for?
std it actually namespace. So
Okay.
our namespace, we
Mm.
define namespace Synthux. Yeah, so all our classes here. I don't know if I didn't do it another way around. Just a second, did I do use? Yeah, okay. So here we are not writing Synthux in the beginning. Why? Because here I said using namespace Synthux. Yeah. So if I put here like using namespace std, yeah, then I can skip this std here. The only thing that this using namespace is okay in implementation files, in CPP files, in inner in this case. But in header files, you don't use this using namespace, because if you header files, they got in they're getting included. Yeah, so so in this case, let's say here I set this using namespace. Yeah, and here I said include scale. What this include means? Include means what compiler will do. It will just take contents of it's not even compiler, it's a preprocessor. So it will just take the content of all this file and just copy it instead in place of this line. That's basically what's going to happen, which means that this command to use namespace std will appear here for whatever reason. And if it somehow conflicts with something or
Yeah.
brings some yeah, so that's why this using is never used actually in headers. Yeah,
But you didn't
so
declare
it's
STD. Did you declare it somewhere?
no std is it's an I imported array already. That's where this array comes from. And in this array, if we look inside, we can look inside. Nice.
I lost you, Vlad. Hold on. So this array, I don't see a file of an array, but you just double clicked on it and now you actually see.
Yeah, I just clicked on
Is the
the
array
array
part of
include.
the Arduino Standard?
No, it's part of standard C++ library. Sometimes those
Okay, so
yeah, so here actually you have this namespace std, so here where it's defined, okay, inside the file itself. And this file is scary. I mean, it's really, I mean, yeah,
this is
it's a lot of
literally the class, like the definition of the array class.
uh no, it's yeah, so basically, but it's like it's not it's not a built-in array, not this array that you just type like this, like int a like 5 or something, or 6. Yeah, it's not this array.
Oh,
It's actually the container that it's this array container. It's around this. It's built on top of this simple array, and it provides a lot of like
okay, additional
um,
functionality.
yeah, it's
Okay,
like convenience.
yeah, okay, so to clarify, this is not something that I need to download. Like I need to
No, no,
download the
no, no,
NPR
no.
one to
It's
one.
there. So if you look here, it comes. Okay, it's STM tools, XP. So yeah, it's standard. It looks like, yeah.
It
So
comes with an
where
installation of
he,
the STM
yeah.
architecture.
So it comes from yeah.
Mm-hmm. Okay.
So basically, you have it. Yeah.
Yeah. Yeah. Okay.
But and those containers sometimes really different like vendors, they do their own implementations like with some modifications, because especially when it comes to like array is like pretty simple container, I would say. Yeah, so it's okay to use with embedded systems. Yeah, but
Mm-hmm.
if we talk about vector, let's say there is another component, container vector. This one in embedded system will not work because it uses dynamic memory allocation. So it's like it's really it needs like what it can do to like put it simple, at some point when it like just it can expand itself. Yeah, so if let's say you define vector and put there 5 elements, then you put another 5, it will just grab some memory and try to like, but on embedded systems you cannot just grab some memory. Yeah, so there are versions of these vectors that use like static allocate, so it just takes from some pool of statically allocated memory. But this is already, I guess, like
Yeah.
more advanced topics, I guess. At least uh, I like working on these instruments. So far I haven't seen like the need to do something like this. Yeah.
Mm.
So usually with just fixed size you can
Yeah.
do go pretty well. Yeah, so ARP class is the biggest one, and again, please watch the previous episodes. There we go through all this in detail. What does it do? So basically, in the root of all this are two collections. These two arrays. One array of nodes, which is more or less like ordered by the node number, which allows to play like up and down. Yeah, so according to. And second one is input order, which is sorted by actually input order. Yeah, so
Yeah.
when the note was which note was played first, and this allows to do this as played. Yeah.
So that in comparison to this. So this is by order, and this is so this is by the order I play, and this is just as a chord like going up.
So yeah, so then Vox is pretty simple, as I already mentioned. It's has just one oscillator with triangular wave.
Is the
I added
LFO active
LFO.
here?
Yep, it just really like just a little bit, just to make it not just like
Are you trying to
to
emulate analog with some glitchy?
yeah, probably. I mean it does like, but this deviation is really small. I don't remember which, but yeah, it's really like LFO yeah, so
Yeah, I
this is
see.
amplitude of LFO, so it's just a little bit. um and yeah, so you and yeah, one envelope, just envelope, just LFO, just oscillator, so just a
Hmm.
um, basic set, and then all those guys are connected together, and they are connected together with those callbacks. Yeah, so I have in main files, I have this different functions. So one of on scale select, on terminal note on, note off, and yeah, this is actually callback of arpeggiator. So that's one of the options how you can connect your classes and make them like easily like replaceable. Yeah, so in this case I just um, change it internals of the terminal, and because it communicates to outside with just by calling this function instead of just explicitly knowing about some class outside and talking to it, it's actually uh, I can like be more flexible in designing things. Of course, callbacks come with additional overhead for calling the function comparing to the direct function call, but it always depends. Yeah, so I usually first try to design for like flexibility for actually for design, and then if I see that okay, it grabs somewhere too much resources, then I can always optimize, and when system is designed properly, it's even easier to find the bottlenecks
Hmm.
usually. So that's basically what's happening here. Then we have all good audio callback, which doesn't have too much because majority of stuff is happening actually outside of it. Yeah, so communication is happening outside with those callbacks. Yeah, that's why audio callback only pulls the audio data more or less. It has also this trigger to metro trigger, but this thing can also go away if you imagine if you connect like external clock. Yeah, so in this case it will even just go somewhere to interrupt handler or something like this. Yeah, and then audio callback will have only the Vox itself. Yeah, in setup we actually just assign those functions, and yeah, and then we have loop where we read all the controls, pod switches, and also terminal as we just seen.
Yeah.
So pretty simple. Yeah, here I use like delay 4 milliseconds. It like another option would be to set some counter like measure milliseconds and just call all this bunch of code on like after like 4 milliseconds, because delay more or less what does it do, it just at the point of at the moment of delay you don't do anything else. Yeah, but anyways, what oh sorry, what I try to achieve here is basically just uh, not check those controls all the time. Yeah, 4 milliseconds is pretty real time. Yeah, I guess I would say probably up to 10 milliseconds is still like feels like real time.
Yeah.
But it saves a lot of like these loop cycles. Yeah, you not save even the cycles. It's not about saving cycles here. It's more about like not querying all the time those controls.
Mm.
Yeah, that's like really quickly quick overview of the instrument itself. Uh, if you if you will have questions, like more questions after watching the previous workshop, looking on the code, you can always ask on here in comments or on Discord.
Yeah, you
I
can
will be happy.
change the camera view
Yeah,
to wrap things up.
probably. Yes. Oh, yeah. Yes, I can. Oh, hey, hi again.
Yeah,
um,
cool. Um,
yep.
yeah, so if I'm going back to the Spotify synth, the way that you're using the sensor there is slightly different, right? Because you actually need more functionality.
Uh, no, what I meant by doing it differently is so here I just directly like I do more or less like low level stuff. Yeah, I mean I can probably quickly try to show what is the difference there. Um,
We don't have to go
just
like too deep into it. I'm
yeah, yeah,
just
yeah,
curious because like the logic that you create there is simply just a bunch of if statements that you add, or do you
yeah.
actually need to go
y-
lower level to make it to optimize it?
No, actually, what I'm doing in Spotify, every pin, every pad has
Mm,
dedicated class, which is a discrete sensor pad. Yeah,
right.
you can see it probably. Yeah, so which gets so what this guy is responsible for is actually actual behavior of the pad. Yeah, so if it behaves as a toggle or it behaves
Mm,
as just a push button. Yeah, so that's basically what this guy is doing. Yeah,
okay.
so it gets its mask, so this which beats it should look for, and it gets also callbacks. Yeah, so with this std function, it's also just a callbacks. And then I have discrete sensor, which has collection of those pads, and I define targets for them. And the difference here, so I mean, we don't need to go into details of this thing, but the thing here is that then in controller, let's say, I talk to my sensor not in terms of pins, not in terms of like beats or something like this. I just talk in terms of target. So I say discrete sensor target A, I want it to be toggle. And the nice thing about this is that in this case, as we just talked, record A and record B, they are not like single pads. Yeah, it's just like this combined virtual pad, which
Mm,
works when you push to when you touch play forward and
yeah.
play backward. And because I have all this system, I can group those, regroup them, change which pad will do what, and on the higher level here in controller, I don't care about it. Yeah, I care only about like I just want this thing to work as a toggle, and that's it. And I know that it will work as a toggle. Yeah, let's say it's actually like next iteration already, because yeah, in original iteration record doesn't work like a toggle. Yeah, it's
Yeah.
just push button. But here, just by defining this one line, I can change the behavior, and so that's basically what I meant. Yeah, so there I made a little bit more like structure on top of it, in order to be able to like manipulate all those paths not in terms of pins or something. So I don't want to care about this. Yeah. So here, this is basically when I read this, and I read just a target. Yeah, I say, okay, I want, if I touch tempo, then please do, no, sorry, it's slice position. It's not, it's not, yeah, here. Yeah, so one shot forward A, one shot forward B. So I don't talk to pins, I talk to just some virtual targets. Yeah, so if I decide that one shot forward A, like it's actually play forward, should be like 2 pads or 3 pads or something. Yeah, I can easily I can change it underneath. So here when I define this discrete sensor, where is it? Yeah, so here basically I also created this macros that I shown in the beginning. Yeah, so let me just quickly, yeah, I mean it's probably already too much details, but this is the macro that we've seen in the example. And then I added another macro together, which actually combines two integers into one. So that's how I can define. And then I just say that, okay, play stop is pin 5. Record A is together, pin 3 and pin 4. Yeah,
Yeah,
so
it actually looks super organized. Like I know that this is on GitHub, right?
yes, it's on GitHub. Yeah.
Cool. So
Yeah, so basically that's what I meant about like doing it a little bit like more like it's not advanced, but just a bit more organized. Yeah.
yeah, yeah, no, that's really nice. So if you guys want to look into the code of Spotify, definitely go to. So this is on your GitHub
Yeah,
account, right?
yeah. But this GitHub is linked on the Synthux Academy webpage, I guess.
Yeah,
Yeah, it
yeah,
should be there. So yeah,
yeah. At a certain point in like hopefully in a couple of weeks, we'll be able to also sell these as kits. So if you'd want to build something like this with the instructions from Vlad and the code and everything, you'll be able to do that as well. At the moment, this is not really available, but this soon will happen. If you have any questions about any of this, feel free to join on Discord and ask questions there. Both me and Vlad are there on Discord. Yeah, please like and subscribe because it helps to show the algorithm that we're valuable for some people. And yeah, if you have any questions, drop them on Discord. Thank you so much for taking the time to be with us, and we'll see you in the next workshop.
thank you.